Es ist für Sie abgegeben worden, Chef.
Good morning, Professor Rieg. The man on this photo is the late German engineer Hermann Pfatter, who invented the Hobbing procedure, which is used all over the world. A Hobbing procedure, which is less universal but much easier to establish, was invented by the American George B. Grant, and this procedure you should use for your hobbing attachment. Hobbing needs a 100% synchronization between hob and workpiece. In video 151 you realize this by two cardan shafts. Your mission, Frank, if you'll accept it, is. Now this synchronization should be made electronically because electronic coupling is much more space-saving and allows larger helix angles. We know that your chances are zero. Should you or your team be captured or killed, we have to deny knowing you. Good luck, Frank. Please destroy this tape immediately.
Now we are building a more permanent solution, especially when it comes to electronics. From the point of view of an electrical engineer, this is certainly quite amateurish, but it works, and that counts. Fire away. The drive must run easily, but almost free of play. Changing the hob. Setting the cutter pitch angle gamma. Gamma is here 1 degree 42 minutes. A video from the 1950s by Pfatter, today Gleason Corporation, on YouTube provides a separate flywheel for the hob to run smoothly. We do that too. Such a dumbbell would be exactly a fancy raw flywheel. Now the electronics. The 400 pulses per revolution of the hub are sent by optocouplers directly to the input of the stepper motor driver. It is set to 400 micropulses per revolution. Thus, there is no need for a microcontroller. Here is the circuit diagram. However, the motor is not a real servo motor. It is in fact a closed-loop stepper motor. Left rotation, yellow LED on. An alarm circuit is still missing. If the servo motor is overloaded, then the milling motor should also be stopped immediately, otherwise the workpiece or the milling cutter will probably be demolished. The servo motor driver has an alarm output, but it just switches the other way around as you think. The signal must be inverted. The frequency converter, on the other hand, expects a switch between S3 and SC to stop the motor. I solved this signal inversion very complex. ALM plus is pulled to plus 5 volts and given to pins 2 and 3 of an Arduino Uno. There, interrupts invert the signal and switch a relay via pin 13, the output of which goes to the Phi. An electrical engineer would solve this much more elegantly, but it works. Frequency converter is in normal operation. Let's see if the alarm goes off. Very well, the frequency converter has stopped. Reset of the driver by mains off. Clear the error status of frequency converter, connect SC to S4. Error status is cleared. Then we can mill the first gear. A blank with a diameter of 93 mm for a gear with 60 teeth, profile shift 0, helix angle 0 and module 1.5. Is not exactly vertical yet. After alignment, good enough. Almost 0.3 of a millimeter deflection, a bit much, align. Loosen these 3 screws to align. Not so bad. Exchange the 40-teeth master gear for the 60-teeth master gear. Here we go. For the second cut, go to a depth of 1.5 millimeters. Third cut to a depth of 2.5 millimeters. Penultimate cut to a depth of 3.3 millimeters. Last cut to 3.6 millimeters. We need, after German standard, a tooth depth of just under 3.4 millimeters. However, there was an offset of approximately 0.2 millimeters. This ripple pattern is perfectly okay. They are so-called feed marks. Have commercial gears too. Not so bad. Comparison with a professionally made gear wheel, from German supplier Modeler. So far so good. The optical comparison looks satisfying, but a precise measurement is better. You can measure the teeth width by computing a number of teeth for testing and then compute the width. Measure this width by a caliper or a special micrometer. Not so bad. Now a helical gear with 60 teeth, module 1.5, profile shift x equals 0 and helix angle beta equals 20 degrees, rising to the right. Make an adapter plate to fasten the gearbox unit on the milling table further inside. Align the gear unit in parallel. Roughly adjust the swivel table. Precise setup and control of the 20 degrees. The machine is ready to go. Speed of the hob is 150 revolutions per minute. This cable is the only connection from hob to workpiece. Now the counterpart, helical toothed sprocket with 60 teeth, module 1.5, profile shift 0 and helix angle 20 degrees, rising to the left. To do this, the device must be moved slightly on the milling table. Adjust to 20 degrees. This scale is too imprecise. Adjust concentricity of the workpiece via 3M8 screws. Here we go. The milling cutter and workpiece turn in the same direction as with right-hand gear, only the workpiece axis is tilted in the other direction. Next cut. We use the grand process here, see video 155. The fodder process is complex and needs a differential gear. You can stop the milling motor after a cut. The electronic coupling stops the stepper motor immediately and keeps its information, as long as the electrical power is not switched off. You are absolutely safe if you let the milling motor and the stepper motor keep running. The milling cutter is moved back in X. You have to do it anyway, and while the milling and stepper motors are still running, you move back to next cut in starting position Z. Last cut. Now the highest level of complexity, a helical gear with 60 teeth, module 1.5, profile shift -0.8 and helix angle 30 degrees, left-handed. Mounting the adapter plate. Align in parallel. Set 30 degrees. Adjust and check concentricity. Last cut. Tooth depth reached. To conclude, a helical toothed gear with 48 teeth, module 1.75, profile shift plus 0.3 and helix angle 30 degrees, rising to the left. Remove the hob with module 1.5 and insert the new hob with module 1.75. Loosen the taper lock for the flywheel. Unscrew the encoder with a plate. Adjust gamma for the hob with module 1.75. Mount the master gear with 48 teeth. This can be attached to any milling machine. Tooth depth reached. Not really bad. Of course, this works with steel, too, as you can see in video 151. What did we learn? In this way, every standard vertical milling machine can be converted into a hobbing machine. Swivel the milling head by 90 degrees. Build a bridge for supporting the arbor. Insert a long milling arbor. Install the encoder. Build the gear with stepper motor. Manufacture electronics. Manufacture gears, straight and helical teeth, with and without profile shift. Isn't that awkward with the master gear? No, that's the only way we can achieve 100% synchronization by simple means. And a single straight-toothed master gear can produce any helix angle from plus 30 degrees to minus 30 degrees or more. Any profile shifts from positive to negative shifts. Any modules. And with the master gear module 1.25 mm 20 dpi change wheels for Myford lathes can be used directly.